Now we've gotten the stars onto the main sequence. Once we have the stars on the main sequence, we're going to split stars into two categories, high mass and low mass. And the reason we do this is we actually start to see some variation between the two types of stars once we get to the main sequence. All stars pretty much all form the same way, but from here on we're going to see some differences. So we're going to begin with low mass stars. Now our go-to example for low mass stars is going to be the Sun. So essentially what we're going to be talking about from here on is the Sun. Stars spend most of their life on the main sequence. We're talking about 90% or so of their life. Now when they first reach the main sequence, they're going to have the usual composition everywhere, including their core. This is that 74% hydrogen, 25% helium, and 1% metals we've talked about previously. Now that's when it first reaches the main sequence. However, as it's on the main sequence, as it goes through hydrogen fusion, it converts hydrogen into helium. What this does is it's going to decrease the overall amount of hydrogen and increase the overall amount of helium. This leads us to our fourth lecture quiz question. What is the equation for the proton-proton chain? A, 4 hydrogen become a helium giving off energy. B, 2 hydrogen become a helium giving off energy. C, 4 helium become a hydrogen giving off energy. Or D, 3 helium become a carbon giving off energy. Go ahead and think about it and we'll discuss in just a bit. Alright, so the equation for the proton-proton chain is 4 hydrogen. We combine 4 hydrogen together and that then gives us helium-4. Now notice that every time we go through this sequence, we actually have 3 fewer particles in the core. We started out with 4 hydrogen and then ended up with only 1 helium. Because we have fewer particles, this means that the pressure in the core is going to decrease, and as pressure decreases, the core is going to shrink. Gravity is going to be unbalanced by the pressure, so the core shrinks. Now, as the core shrinks, it's going to increase in density and increase in temperature. Because we have a higher density and a higher temperature, this is then going to lead to a faster fusion rate. We're going to be fusing things faster than we did before. Because we have a greater fusion rate, this is then going to lead to a greater release of energy, increasing the pressure through the rest of the star. And as the pressure increases, the rest of the star is going to expand. It will also get a little bit hotter and a little bit more luminous. So, as an example, looking at our Sun. The Sun has been on the main sequence for around 5 billion years. And in that time, the Sun is now about 40% more luminous, 6% larger in radius, and about 300 Kelvin hotter than when it first got to the main sequence. So it has increased by a little bit in all of these ways. Once the core has used up all of the hydrogen, the fusion in the core is going to end. The core has now been converted from hydrogen completely into helium. There's no hydrogen remaining in the core. However, there can still be a shell of hydrogen fusion surrounding that core. This, where we have a shell of fusion, is known as shell fusion. When the core no longer has fusion pressure, so that fusion pushing back out, that pressure goes away, the core is then going to begin to shrink. Gravity is going to win. And it's going to continue to shrink until it gets squeezed so tight that electron degeneracy pressure takes over, pushing back against that crush of gravity. Now, as that core is shrinking, the shell is also going to be moving in, which is going to cause it to get compressed more and also heat up more. Because it has a higher pressure and a higher temperature, that's going to lead to a faster fusion rate within that shell. Okay, well, with a faster fusion rate in the shell, that's going to increase the pressure throughout the rest of the star, so the rest of the star is then going to expand. So again, notice that the core shrank and the rest of the star then expanded. Now, as the shell fusion continues, it's going to convert hydrogen into helium, and then that helium is then going to sink onto the core, causing the core to again begin to shrink a little bit. What this is going to do is cause the core to continue to heat up until it reaches around 100 million Kelvin. As the core is contracting, this means that the shell surrounding it is going to get compressed more, so that this leads to a higher temperature and a higher density, which means it's going to get a faster fusion rate. Therefore, the core is going to produce more energy, which means that there's going to be a greater pressure throughout the rest of the star, causing the entire thing to expand. As the star expands, it's going to expand up to 100 times its main sequence size. Now, using our Sun as an example, our Sun currently has a radius of about 1/100th of an AU. So when it reaches this size, it's going to be around 1 AU. Now, if you remember back, an AU is the average distance between the Sun and the Earth. So the Sun will swell up until it fills the orbit of the Earth. Now, there's some debate whether it's going to be just under 1 AU or just over 1 AU, but for anything that's still on the Earth, it doesn't really matter. Either way, it's going to be a very bad day. Now, because of how far away the surface is from the fusion core, the surface cools off, so it becomes reddish in color. So we refer to these as red giants. Red because it's red in color, and giant because it's really, really big. Now, as we look at what's happening on the HR diagram, when these low-mass stars leave the main sequence after they have finished fusing the hydrogen to helium in their core, they're going to swing over to the right, becoming cooler, but as they get larger, they're going to become more luminous. So this right through here is what we refer to as the red giant branch. This is where we find the red giants as these low-mass stars have left the main sequence.